Hello, welcome to this presentation. I'm Giuseppe Sanfilippo from University of Palermo. This is a joint presentation with Niki Pfeifer from University of Regensburg. Niki will be the speaker of this talk. Let's go, Niki.
Thank you. So our talk is about probabilized Aristotelian syllogisms as a rationality framework for quantified reasoning. The outline of the talk will be as follows. We will present the probabilistic semantics for Aristotelian syllogisms. We will first explain the sentence types, figures, and validity in probabilistic terms. Then we go through all three figures by examples. Then we study imprecise Aristotelian syllogisms. There's syllogisms with generalized quantifiers. And then we make a bridge from ancient Aristotelian syllogisms to modern non-monotonic default reasoning. Our approach is based on coherence. Coherence goes back to Bruno De Finetti. And the key thing, one of the key things is that probability is conceived as a subjective one. So the probabilities are degrees of beliefs. In betting terms, a probability assessment is coherent if and only if in any finite combination of n bets, it cannot happen that the values of the random gain are all positive or all negative. In a nutshell, you need to avoid Dutch books. The coherence approach does not require a complete algebra. While many approaches define conditional probability by the fraction of the joint and the marginal probabilities, which need to assume that the antecedent, the conditioning event must have a positive probability, we do not make this assumption. In our approach, conditional probabilities are defined as primitive, and we are able to properly manage even if the antecedent has probability 0. Probability logic in the nutshell means the study of uncertain argument forms. The consequence relation remains deductive, and it is about propagating the uncertainties from the premises to the conclusion. So our motivation is as follows. First, we want to recover qualitative principles within the quantitative framework of coherence-based probability logic. Specifically, we are providing a new coherence-based probability semantics for Aristotelian syllogisms. And we build bridges to generalized quantifiers as well as non-monotonic reasoning. So just to recall, the basic syllogistic sentence types involved in syllogisms are the universal affirmative, or every S is P, some S is P, no S is P, and some S is not P. In predicate logical terms, you see here the formalization, and in blue, this is the existential import assumption, meaning that the S term must not be empty. This will be important in a minute. In Aristotle's Analytica Priora, he studied the first 3 figures only, and also our work is restricted on the first 3 figures. We will ignore the 4th figure in our presentation. As an example, consider as an example of a syllogism of figure 1, consider most famously modus barbara. Every M is P, every S is M, therefore every S is P. Here you can see listed all the Aristotelianly valid syllogisms of figure 1, 2, and 3. They differ in the term order, and here with the asterisks, these are those which are traditionally requiring the existential import assumption for validity. There is just to have a look at the literature, a brief one, there is a long and ongoing tradition in the psychology of reasoning, actually since the first experiments on deductive reasoning by Störing and Lindworski. Probabilistic versions of syllogisms in the history of philosophy can be found, for example, by Lambert. This is probably the first instance. Boole, De Morgan, and Heilpering gives a nice historical overview. There are also frequency interpretations, for example, Peterson's intermediate quantifiers, Murphy's exceptive quantifiers, and generalized quantifiers in terms of conditional probabilities, what we will do, has been studied by Cohn in linguistics, for example, and most famously in the probability heuristics model by Chater and Oxford. Now, how are the sentences interpreted probabilistically? Every S is P, for example, is interpreted by a corresponding conditional probability equal to 1. No S is P means the conditional probability of P given S is 0. And some S is P is just the positive probability of P given S, and some S is not P. Accordingly, the probability of not P given S is positive. Here, in the coherence approach, we do not presuppose that S has a positive probability. This will be important for the existential import. Here you can see the logical square of opposition generalized towards probabilities. In the corners, you see the basic syllogistic sentence types and the logical relations among these basic syllogistic sentence types. For example, every S is P is contradictory to some S is not P. So now let's have a look towards the validity of the probabilistic modus barbara. Here is a formalization in terms of these interpretations of the basic syllogistic sentence types. As you can see here, this version of modus barbara is probabilistically non-informative because the premises do not constrain the probability on the conclusion. If the probabilities of the premises is 1, 0, 1 is coherent. Therefore, and this is also the case for all three other figures, all syllogisms of all three other figures, they are probabilistically non-informative and hence not valid. In our semantics, we show that all Aristotelian syllogisms are valid if we add suitable existential import assumptions. Let's have a look at the difference between our approach and the probability heuristics model. The probability heuristics models assumes the conditional independence of between the n terms, that is S and the P term, given the middle term. So this is the assumption that is made in the probability heuristics model, besides the assumption that the conditioning events must have a probability that is positive. So a sample reconstruction of modus barbara would be as follows. Here we have the major and the minor premise with the according existential import assumptions. That is the assumption that the antecedent has a positive probability. This is the conditional independence assumptions. And from these premises, you can obtain that the probability of the conclusion is 1, which validates modus barbara. Note that in our approach, we do not make these assumptions here. We do not assume that S and M have positive probability in the coherence framework. If we do not make this assumption, we obtain that, again, this argument form is probabilistically non-informative. This means the conditional independence assumptions without assuming positive antecedent probabilities does not help. It is not valid and it is probabilistically informative, as you can see here. So we give another interpretation of an existential import, which is weaker than assuming positive antecedent probabilities. That is, we call it a conditional event existential import assumption. For example, for figure 1, it is the assumption that S given S or M is positive. And this is weaker than the positive probability of S. Concerning the validation, we follow the following strategy. We computed the probability propagation rules for all three figures. All Aristotelian syllogisms are validated by respective instantiation. For example, look at the probabilistic version of modus barbara. Here we have the premise set, here we have the conclusion. The premise set consists of the major and the minor premise, and here in blue, our existential import assumptions. From this, we can prove that the conclusion holds. So every M is P, every S is M, therefore every S is P. Likewise, we obtain the probabilistic modus barbari. And here you can see the general form of figure 1 or the probability propagation rules for figure 1. So here we have the associated conditional events. Here is the conditional event for the major premise, here for the minor premise, here is the existential import. This one is assumed to be positive, and this one depends upon which quantifier you have. So we have the value X for the major premise, the value Y for the minor premise, and T just assumed to be positive for the conditional for the existential import assumption. And in this formula, you can see here how you compute the lower and the upper bound on the conclusion. For example, in figure 2, we proved camestres, camestrop, and all the other syllogisms which are Aristotelianly valid. And here we have the corresponding probability propagation rule for figure 2. By respective instantiations, the validity simply pops out for all the syllogisms. Here you have a graphical depiction of the probability propagation rule of figure 2. And what's important here is that you see here, this surface denotes the coherent upper bound, and this denotes the coherent lower bound on the conclusion. And everything which is between these two surfaces are coherent probability assessments. Here are two examples from figure 3. The probabilistic Tartese is this one, and it is valid. The probabilistic Ferrizon is this one, and it is also valid. Here is the probability propagation rule for figure 3. Again, here you see how you propagate to the lower bound on the conclusion based on the premises, and here you see how the upper bound is calculated, the coherent upper bound, of course. As you can see here, we have point value assessments on the premises, but we also generalized this also for the other two figures for interval valued premises. So that would be the lower and the upper bound on the major premise. That would be the lower and upper bound on the minor premise, and this one on the existential import. And here you see how you propagate onto the lower bound on the conclusion and onto the upper bound of the conclusion of the respective syllogism of figure 3. Here is an example how we exploit this result in order to deal with generalized quantifiers. For example, all P are M would be the first premise. That is an ordinary premise. This one is one involving generalized quantifiers. At least most S are not P. And from this, we can prove at least most S are not P. For example, the generalized probabilistic syllogism of figure 2 would be formalized in this way, and let Y, the threshold for the generalized quantifier in the minor premise, be 0.7. Then we obtain the following version. So all M are P would be just as formalized previously. The conditional probability of M given P is 1. At least most S are not P. That is the generalized quantifier in the minor premise, that is not M given S is greater than 0.7 and at most 1. Here is our existential import assumption, just again assuming that it is positive. And here we have the conclusion from these three premises. You can prove that not P given S is at least 0.7 and at most 1, which validates this syllogism. Now we build a bridge from ancient syllogisms to modern non-monotonic reasoning, to default reasoning, in the following sense. We interpret the basic syllogistic sentence types in terms of defaults and negated defaults. Negated default is, for example, it is not the case that P is a plausible consequence of S. And likewise, a default is P is a plausible consequence of S, or S normally P. And here we have, it is not the case that S normally P. And as you can see here, we have all four basic syllogistic sentence types in terms of defaults and negated defaults. This allows us to show the validity of a selection of default rules in non-monotonic reasoning. For example, modus barbara in terms of default is just the same as weak transitivity, which was studied in the literature. And here we propose a long list of other new inference forms for non-monotonic reasoning, which are valid. This concludes our talk. We presented the coherence-based probability semantics for Aristotelian syllogisms, which respects the logical structure of the argument forms. So we take care what is the major premise, what is the minor premise, what is the existential import. It uses very weak existential import assumptions. They are weaker than assuming positive antecedent probabilities of the antecedent, which is in other approaches necessary in order to define conditional probabilities. In our approach, conditional probabilities, as I mentioned, are primitive. And our approach allows for dealing with generalized quantifiers. For each figure, we prove the probability propagation rule, and validity is shown by respective instantiations. We build a bridge from ancient syllogistics to recent non-monotonic reasoning, and our semantic can be used as a rationality framework for human reasoning about quantified statements. Future work will be devoted, for example, to investigate the probability propagation rules of figure 4, which are not contained in original syllogistic by Aristotle, but which were developed later in the medieval times. And we will also study more generalized quantifiers and build further bridges to non-monotonic reasoning. Here you can see the literature that we mentioned, and I would like to thank you very much for your attention.
Thank you. Bye-bye.